from last week. Oh, actually, we ended up with this, didn't we? So this is where we ended up. We were talking about rewriting an absolute value function as a piecewise function, which is always a really good thing to do. People get really confused when they deal with not just calculus, when they deal with applications or situations involving absolute values, because they are a little bit perplexing, but it's a lot easier to deal with them if you just break it into a piecewise function and then deal with the piecewise function piece by piece. So we established that the absolute value of x is equal to the piecewise function with behavior x when x is positive, the opposite of x, or negative x, when x is negative, and it would equal 0 when x is 0. And so then we used that to evaluate a little more complex function. What if we had the absolute value of x divided by x? Well, then all we have to do is just take each of the pieces in the previous function and just divide each piece by x to see what we get. So we'd end up with x divided by x whenever x is positive, which is equal to 1, right? We would have, the piecewise function would be undefined at 0 because you can't divide by 0, right? Okay. And then we'd end up with negative x divided by x, which is equivalent to negative 1 when x is negative. And so anytime you have the function f of x equals the absolute value of x over x, or x divided by the absolute value of x, that's the graph you're going to get. It's just got infinitely long, it's a step function with only one step, right? You just get a break in the function at 0 where it's undefined, and to the right of 0, the value of the function is 1. To the left, it equals negative 1. So then it gets really easy. Give me thumbs on that. Does that all make sense? Stuff we covered last Friday, okay? So then it's really easy to deal with situations like this. What if f of x is 3x over the absolute value of x? Well, that's the same thing as 3 times the absolute value of x over x. If I multiply a function by 3, what am I doing? How am I transforming the graph of a function if I multiply a function by a constant? Yeah, I'm just stretching it by that factor, aren't I? Right? So then what's the graph of this going to look like?
It's okay.
What's it going to look like? Okay, so y would equal negative 3 going to the left with an open endpoint, right? And to the right, it would start at positive with an open endpoint and go to the right. Make sense? Okay, so now I just want to know, I don't even want to know what the order is. Just tell me, what is the polynomial that models the end behavior of this function? What is it? 3x, yeah. Right? How come? Because we're looking at the ratio of the leading terms. Right? If we're approaching, end behavior means we're approaching infinity, right? Okay, so do I have a... Right, so we end up with this then. So we just get the limit of 3x. So that is the polynomial that models the end behavior. Now, does it mean it's going to be an exact match? No, but it gives me the basic shape. So how would you describe that function, 3x? Draw it with your arms. What's that do? Yeah, it just goes like that, doesn't it? So then what's that tell you that as x approaches positive infinity, what would the function approach? Positive infinity, because it's going up, right? As x approached negative infinity, what would the function approach? Negative infinity, based on the power function model of that rational function, right? Give me thumbs on that. Does that make sense? Piece of cake, okay? How about that one? What's the power function that models the end behavior of that function? Yeah, right? The power function that models it is y equals x. So same thing. As x approaches infinity, the function approaches infinity. As x approaches negative infinity, so does y. Okay. How about that guy? X, again. Anybody see that? Just because, and again, where are we getting it? Just right here. Whoops, not there. Right? Okay? No big deal. Oops. So again, what do we notice here? Maybe you guys picked up on this, maybe you didn't, but I'll just point it out. So for a rational function, if the degree of the polynomial in the numerator is exactly 1 greater than the degree of the polynomial in the denominator, when I take the ratio of those leading terms, I'm getting the power function that models the end behavior is x to the first power, so it's linear, right? Okay, that gives us some unique opportunities. I'm going to look at maybe one more of these real quick before we jump into that idea. What if I had how about that one? What's going to be the power function model for that one? 3x squared, yeah. So that's going to equal the limit of 3x squared as x approaches plus or minus infinity. So now we would see end behavior that would look like that, right? Up to the left and up to the right. Everybody good? Okay, but in this unique case, where the numerator in the top is exactly 1 greater than the numerator in the bottom, we end up with a linear model, and lines are so easy to deal with that we can do something interesting here. We can come up with an asymptote that's very useful that's not a horizontal asymptote. We actually did this. Do you guys remember talking about slant asymptotes or oblique asymptotes a couple of years ago? Okay. Did you do it last year too, probably?
Yeah, a little.
A little bit? Okay, we did it. I know we did it in my class a couple of years ago. How about this one? What's the domain of this function? Can't be 2. Yep. So what happens at 2, x equals 2? Vertical asymptote or whole? Vertical asymptote, because 2 is a unique 0 of the denominator. Okay? So we get a vertical asymptote at x equals 2. Do we get a horizontal asymptote? No. How come?
Degree is higher.
Top's higher degree than the bottom. Okay, so if we want to know what's going on here, we know what the end behavior model is. It's going to be linear. The model is 3x squared over x, which is 3x, but we can do better than that. We can come up with an exact equation of the asymptote by just simplifying this quotient. Do you remember how we did that a couple of years ago? What did we do? We just divide it. Exactly. We're just going to simplify the quotient. Now, what would be the simplest way to simplify that quotient? Do we want to use long division? We could, of course. We'd use synthetic. And why is synthetic an option here in this case? Because the bottom is in the form x plus or minus a constant, right? That makes it a candidate for synthetic division, okay? So then let's do this synthetically. Let's remind ourselves how that works. So to simplify this quotient, To simplify this quotient, what goes out front? 2 goes out front. Not negative 2, 2. How come? Because what goes out front? The 0 of the denominator. Okay, good. So then this is telling us that we get a 2 out front. What goes in the top row of our synthetic bracket? 3, 0, 0, right? Because we need to have coefficients for every power of x, starting with the greatest power of x down to the constant. And then what do we always put under the constant? Our remainder box. There you go. So this is pretty easy to do synthetically. Remind me, how do we do this again? Drop the 3. Anytime a number pops below the bracket, we multiply and add. We do the opposite of long division. Long division, we always end up subtracting vertically. Synthetic division, we do the opposite, we add. So we end up with 3 times 2 is 6. We add those and we get 6. Then we just do it again, right? 6 times 2 is 12, and we add those. And so what does that tell us then? That this is equal to? Okay, good. This is the constant, so that would be the coefficient of x and so on. And that's the remainder, which is what remains over the denominator. So we get 3x plus 6 plus 12 over x minus 2. Okay? Now in the limit, this is the great trick. Okay, you'll remember this. The limit of f of x as x approaches plus or minus infinity is the limit of 3x plus 6 plus 12 divided by x minus 2 as x approaches plus or minus infinity. Which of those terms disappears in the limit? Yeah, right? The quotient. You always, if there's a remainder, always the denominator in that remainder is going to be a higher degree than the numerator. Guaranteed, has to be, right? So in the limit, that term gets extinguished to 0, and you end up with, that's the line that's left over. So that is the exact equation of the slant asymptote. This thing is going to cling to the line 3x plus 6 at the tails of the function. Okay? So we can see that. If we graph this thing on Desmos, okay, so let's graph this. F of x equals 3x squared divided by x minus 2. Okay, so we said, now look at this picture, right? We said that this thing has a vertical asymptote at x equals 2, which it does, right? We can now see that if I graph the line x equals 2, that's the vertical asymptote. Right? There it is. Everybody agree? Okay, we said the slant asymptote was going to be 3x plus 6. Hey, what do you know? Everybody agree? Okay, that's pretty cool. So then, again, the asymptotes are like the bones or the skeleton of that function when we sketch it. We know they have to stick to that as we approach 2 for the vertical asymptote, and as x gets really big in the positive or negative direction, we're going to stick to the slant asymptote. It doesn't really give us a lot of options. It really narrows down the possibilities for this thing. Okay? That make sense? Okay? I'll take a picture of that.
When we get out.
In when? 4 minutes? Okay, let's probably, should get a little time to work maybe. Okay, so you guys review for me. What are the important things we said yesterday? Sum it up.
Infinity. Something about the degree of the ratio of the leading coefficients. Let me look at my
True.
notes.
True.
There can be two horizontal asymptotes.
Could be, right? We looked at one case where there were two different horizontal asymptotes, one left and one right. That can happen.
If the degree of the numerator is exactly one more than the degree of the denominator, then it's linear.
Good. Okay, if the rational function has a numerator whose degree is 1 greater than the denominator, then you know that the asymptote is going to be linear. It's going to be a slant asymptote or an oblique. Sometimes they call it an oblique asymptote. Same thing. We know that slant asymptotes and horizontal asymptotes would be things we would find at infinity. So we'll take limits as x approaches positive or negative infinity. Vertical asymptotes would occur where? At a value of x where would you get a vertical asymptote? Where what equals 0 and what doesn't equal 0? Denominator does, numerator does not. Good. All right, we're getting it. So what I want to look at today is this is going to be kind of a review of just some algebra that supports this calculus. So let's analyze this function. Okay, what's the domain of this function? Yeah, all values of x except negative 18. What's happening at negative 18? There's a vertical asymptote because 18 is a unique 0 of the denominator, right? Okay. So, yeah.
I don't know if it's a vertical asymptote or a hole.
Because if 18 is a 0 of the denominator but not the numerator, that's a vertical asymptote, guaranteed.
It's a 0 of both.
Well, if both are 0, then you have to resolve the indeterminacy. Yeah. Yeah, you can just see it's not. I mean, you can see that 18 is not a factor. We could factor the top, right? The top factors into x minus 17 times x plus 1. And so negative 18 is not a factor of the top. But you could also just plug it in. You can see it's not going to give you a 0 on the top. So the domain, x is not negative 18. We get a vertical asymptote at x equals negative 18. And now you tell me, is it going to have a horizontal or a slant asymptote or neither? Slant. How would we find the equation of the slant asymptote here? Synthetic division. We simplify the quotient with synthetic division. And what goes out front? What goes top row? Remainder box. Okay. And what do we get? Something. Okay, so it doesn't really matter. We're just going to get this whole thing is equal to x minus 34 plus some number divided by x plus 18, right? But in the limit that x approaches infinity, the limit of f of x as x approaches plus or minus infinity then is going to equal the limit of x minus 34 plus some number divided by x plus 18. And we know that that's going to shrink to 0, right? So our slant asymptote then is right there. We get a slant asymptote at y equals x minus 34. And we got it. Okay, make sense? Okay, so what about one like that? What's the domain? What is it? It's all reals, yeah. How come? Denominator has no zeros, no real zeros. Okay, so it's all reals. Do we get vertical asymptotes? Can't, because there's no zero of the denominator, right? Are we going to get horizontal or slant asymptote? Okay, how are we going to find it? Long division. So probably we want to review that a little bit, right? Okay, so let's do a little long division. So we're going to divide what goes inside? Top. Okay, how am I going to write that? X to the 7th plus 2x to the 6th plus what? 0x to the 5th, right? Remember our rules for long division. You have to preserve a column for every power of x. You have to include zero coefficients. So we're going to get plus 0x to the 5th plus 0x to the 4th plus 0x cubed plus x squared plus 0x plus 2. What goes out front? X to the 6th plus 1. Okay, and how do we play this game? Yeah, we're gonna simplify the quotient of the leading terms, right? So essentially, we're just asking leading term inside divided by leading term outside, which means leading term on top divided by leading term on bottom, right? So that gives us, if we do that, what? We get x to the 7th over x to the 6th gives us x, right? And I guess technically I probably should put that clear over there. Doesn't really matter. But we'll put it in the x column. How about? So what do I do with that x? Good. I'm going to multiply by what's the denominator, what's outside. So if I distribute that, I'm going to get x to the 7th plus x, right? And then what do? I subtract. And remember how I taught you to do this. You're going to put a negative outside, put it all in parentheses, and then you just subtract vertically, right? So those guys cancel. This gives me 2x to the 6th. I get my 0 x to the 5th plus 0 x to the 4th plus 0x cubed plus x squared. 0x minus x is negative x plus 2. Okay, now what? Okay, what do I get? 2. Leading term inside divided by leading term outside is 2. Distribute the 2, and we get what? If I distribute the 2, we're going to get 2x to the 6th, and then I'm just going to get plus 2. And I'm going to subtract the whole thing. And that's going to be my remainder, isn't it? Anything I'm left with. Okay? So that gives me x squared minus x, and those guys cancel. So that's my remainder. So then this whole thing, f of x, is really just equal to equals what? X plus 2 plus
x squared
x squared minus
minus x over
x over my denominator, x to the 6th plus 1. So in the limit that x goes to infinity, what's going to happen to the remainder term? It's going to go to 0 because it's a rational function where the denominator has a higher power of x. It has to be that way, right? So this tells me then that my slant asymptote, I get a slant asymptote at y equals, what was it, x plus 2? Everybody good? Make sense? Okay.